My name is Chaim Weizman. I'm one of the co-chairs at Columbia University. I'd like to extend my warm welcome to all of you for joining the EMI conference. I hope that in the near future we can all meet in person and we can kind of see each other and interact directly rather than through Zoom. But in any way, this is the current situation, so we have to do our best. So the next plenary lecture will be given by Professor Arif Masud from the University of Illinois in Urbana-Champaign. And the introduction to Professor Masud will be given by Professor Roger Gannon from USC.
Good morning. I'm delighted to introduce our next keynote speaker. Arif Masud is professor in the Department of Civil and Environmental Engineering and in the Department of Aerospace Engineering at the University of Illinois, where he also holds the John and Eileen Blumenschein Professorship in Mechanics and Computations. He received his bachelor's degree from the University of Engineering and Technology in Lahore and his PhD in computational mechanics from Stanford. Professor Masud is a pioneer in developing new paradigms in computational science to solve emerging challenges in solid and fluid mechanics. In particular, his work on stabilized methods and variational multiscale methods provided critical insight into closure arguments and paved the way to applying computational methods to increasingly complex engineering problems. Professor Masud has served the EMI community for a number of years, both as chair of the Computational Mechanics Committee, as associate editor of the Journal of Engineering Mechanics, and more recently, as member of the EMI board. He has also served on the Executive Council of USACM and currently serves on the board of directors of the Society of Engineering Science. Dr. Masud is a fellow of USACM, IACM, AAAM, EMI, ASME, and SES. He was awarded in 2019 the G.I. Taylor Medal from SES. Without further ado, here's Professor Masud talking to us about exciting work at the interface of hierarchical and data-driven modeling of coupled systems.
Thank you, Roger, for the very kind introduction. I would also like to take the opportunity to thank EMI for inviting me for this lecture today. I'm deeply honored and I profoundly thank the Institute for this opportunity. The topic of my talk is hierarchical variational methods for coupled field problems, data-driven modeling, and error estimation. And I'll present ideas in the context of developing numerical methods for nonlinear problems with coupled interacting fields, dominant scale effects, and interfacial phenomena. This slide shows examples of multiscale and interfacial problems in solids and fluids while accounting for thermomechanical couplings. Here we have, on the left, we have multi-constituent material model, stiff inclusion in a soft matrix with discrete interface that develops strong discontinuities. We can have phenomena that are governed by overlapping equations, chemically reacting fluids permeating through porous elastic solids with dominant interface that traverses through the domain across which the material properties change. These problems are of relevance in reservoir simulation, in oxidation of materials, as well as in drug profusion in tissue engineering and tissue modeling. With additive manufacturing, where depending on the timescales of the layering process and the intrinsic timescales of the curing of the material, weak planes are formed with residual stresses. And these planes can grow into failure planes under cyclic loading. We have fluid structure interaction with a dominant interface across which governing equations, governing models are solid mechanics or fluid mechanics. Or we can have artificial interfaces that represent the geometry of a complex shape around which we want to do fluid mechanics. And an advantage here is that the geometry doesn't have to be aligned with the measurable lines. Rayleigh-Bernard instability involving thermal and mechanical fields all the way into turbulence. Again, overlapping governing equations governing the evolution of the physical and the thermal fields here. So these are all different classes of problems. And this conference, EMI conference, I see symposia that are addressing one or the other of these problems. But from a mathematical method development perspective, I like to highlight the common features of these problems. They're all governed by multiple simultaneous PDEs, whether they are across interfaces as in fluid-solid interaction or multi-scale, multi-constant material modeling, or they are overlapping as in the case of porous media flows or in fluid mechanics. And since there are multiple physical phenomena, each with its inherent spatial, material, and temporal scales, so these are highly scale dependent. So these give rise to mixed field problems. And because of the interfaces that can induce jumps in the fields, there is a further classification, mathematically non-smooth mixed field problems. So a question arises, what should be the mathematical constructs of the underlying numerical methods so that they can address this range of issues that we see here? And what can one say about the stability and accuracy of the methods in the general nonlinear range? I'll try to address some of these topics in my talk today. Here is an outline of my presentation. I will first present the variational basis of the variational multi-scale method, the mathematical constructs underlying it, and extend it to coupled field problems involving multiple PDEs. Then we will develop a framework for classes of problems that have weak or strong discontinuities by embedding ideas from discontinuous Galerkin method within the variational multi-scale framework, giving rise to VMDG class of methods. These methods come equipped with built-in error estimators, and we will use, with the example problems, I will show these mathematical attributes of the method. We are living in an era of big data. So one objective of developing the methods is to see if we can embed data into our model-based simulations. I'll show that the mathematical constructs of the method that I'm going to show here, it has regression feature built in it that can be exploited for embedding sensor or experimental data in simulation process. I'll present these ideas in the context of material modeling, multi-constituent materials, finite strength thermomechanics with weak and strong discontinuities. And we will extend these ideas in the context of interfaces and fluid structure interaction with the objective of developing methods that can accommodate incompatible discretizations. Then I'll talk about overlapping PDEs with concurrent scales in the case of density stratified flows, and present VMS application for deriving closure models. So the main emphasis of today's talk is going to be on method development, and we will be looking at the different technical issues that I presented on the previous slide as the motivation and the driving mechanism for developing a robust method. So let's look at the variational foundations of the multi-scale methods. Here is a model problem. L is the governing operator acting on the unknown function. For solid mechanics, these are the equations of elasticity. For fluid mechanics, these are going to be the operators of the Navier-Stokes equations. So we define the appropriate weighting functions, integrate it over the domain, and this becomes the basis of the Galerkin method. We make mesh and try to solve the problem. Now, mesh, depending on the resolution capacity of the mesh, we are able to capture features in the total solution that are larger than the characteristic size of the mesh, and features that are smaller are lost. So with a given good method and spatial discretization, we'll be able to capture the mean solution, but the fluctuations will be lost. Fluctuations, if these are important, then we need to refine the mesh. So the question right now is that we ask ourselves, is it possible that we can develop a numerical method which can use cruder discretizations and still be able to represent the effects of fine scales onto the coarse scales? So if we look at this decomposition, so total solution has a part which is computable and a part which is beyond the resolution capacity, it is an error. Error is also a solution to the governing equation. If this equation is nonlinear, then this scale decomposition should be looked at in the sense of projections. weighting function is arbitrary, so we can likewise split weighting function into coarse and fine scales and substitute it in the weak form, and this gives us multi-scale form where all the scales are fully coupled. Now, employing the linearity of the weighting function slot, we can split this problem into a coarse scale problem weighting by the coarse scale weighting function and a fine scale problem which is weighted by the fine scale weighting function. And the key idea here is to solve the fine scale problem and extract an expression for the fine scales that then can be substituted into the coarse scale form. So we will spend time on looking at fine scale problems, and I'll use different model problems, different problems from mathematical physics to illustrate this idea. Now think of it that we are solving a nonlinear problem, so we go from step n to n plus 1. So U bar is a computed solution from the previous step. We can take it to the right-hand side, and that gives us the residual of the Euler-Lagrange equations, and that drives the fine scales. So fine scales are in fact driven by the residual of the Euler-Lagrange equations. And in this derivation, the structure of the stability parameter appears naturally, that I will show. We substitute this back into the coarse scale problem, gives rise to this modified form where the terms in the black are the Glerkin terms, and these two terms have appeared. They are now modeling the effects of the lost physics. So what I want to point out here is that VMS method is not just a method to stabilize the numerical scheme. It is also a method to build in the physics which was otherwise going to be lost on cruder discretizations. And this method also has the error estimation feature. So we will revisit the fine scales in the example problems that I'll discuss to show how to exploit the fine scale error estimation feature of the method. Our objective is multiple PDEs. So let's look at in the context that we have two different PDEs across the interface, and this is typical for fluid structure interaction. And this is also in multi-constituent materials. If you have one of the constituent that is incompressible and therefore is better represented by incompressible form of elasticity. But incompressible form of elasticity comes with additional unknown field, pressure field. So two different PDEs across the domain. Before we do that, let's look at a formulation that governs or that accommodates the discontinuity. So we take a knife and we cut the domain into two parts. So governing equation, operational inside each of the domains. And since the functions are cut, so we have to impose the continuity of the forces and the continuity of the field itself. So we can do that by utilizing the Lagrange multiplier method ideas, imposing the continuity of the flux and continuity of the field. Now, Lagrange multiplier makes it a mixed field problem, and mixed field problems are subject to discrete in-soup conditions when we numerically solve them. So question is it possible that we can recover an expression from Lagrange multiplier? Is it possible that we can do that? And this Lagrange multiplier is appearing at the interface. So we use the idea that I showed on the previous slide of additive decomposition of the total solution. And here the argument is that since we are imposing the continuity of the field in a weak sense, so there will be some numerical error. So U prime can be looked at as error in the exact enforcement of the continuity of the fields. And when we solve it locally at the interface, and I'll show with example problems, we get a structure that looks like this. So what's important here is to look at the structure. We have Glerkin terms, domain interior terms. The top two blue terms are the terms coming from the DG method. They're present in the DG method. But through the VMS-based derivation of the interfacial formulation, we get these two additional terms. This is the stabilized term for the flux and stabilized term for the displacement field. I will focus on these two in the examples that I show. So let's look at the strong displacement form of elasticity and impose a discontinuity in there. So we cut this domain. So we now have to impose the continuity of the field and the flux, which we do through Lagrange multiplier. Now, Lagrange multiplier method, Lagrange multiplier has the connotation of a force type field. And so it tells us how much force is required to keep the two parts together. But if this interface has kinematics, if there are two solid bodies which are sliding past each other, Lagrange multiplier cannot modulate. Penalty function method cannot modulate. So we need to embed physics. How can we embed physics at this interface? That is one of the design objectives of this method development aspect. Then there are Nietzsche type methods that are also displacement based formulations, but they come with parameters, Nietzsche parameters, and evaluating those Nietzsche parameters in the general nonlinear range is neither straightforward nor very well defined how to do that. So we will rather develop a method, a VMS method, extended with embedding DG ideas in it to model this class of problems. So we do a decomposition of the total displacement field into coarse and fine, and that gives rise to a coarse scale problem and a fine scale problem. Since we have not assumed a decomposition of the Lagrange multipliers, so continuity equation only contributes to the coarse scale part of the problem. So we are going to focus on the fine scale problem, and the general framework is here. We localize the fine scale problem to a strip along the interface, and in the context of finite element method, this is the first layer of elements on either side of the interface. We are going to employ the bubble functions approach, which is generalization of the residual free bubbles idea. And locally solving for the fine scale equation, we get we can extract expression for Lagrange multipliers, which can then be substituted in the coarse scale form, and that gives us our stabilized interface formulation. And I will now show it with the help of a couple of example problems. So let's take a look at the fine scale problem, where we have opened the continuity of the flux term. We represent the fine scales with their bubble functions or edge functions. These functions are non-zero along the edge for which they are defined, and they become zero at all the other edges of the element. And we through this, we can also accommodate non-matching meshes. And for that, the only thing that we have to do is that we project the nodes onto the common interface, find the segments, and solve this problem segment-wise along this interface. And when we locally solve this, we get an analytical expression for the fine scale displacement as shown here. It's important to note that fine scales are proportional to the residual of the flux at the boundary. In addition, the parameter tau, stabilization parameter at the interface, is analytically derived, and it is a function of the operators of the equation, governing equation, acting on the fine scales, which are represented in terms of the bubble function. So the bubble functions only reside in the definition of the stabilization parameter, which is analytically derived. And in here also lies the constitutive tensor. So this is fully aware of the geometric and material evolution of the problem. Now we have fine scale fields at the interface. Lambda Lagrange multiplier is also an unknown. So the question is it possible that we can also find the Lagrange multiplier? For that, we go to the coarse scale equation, coarse scale continuity equation, which has jumped in the displacement field. Displacement field has a coarse part and a fine part. We open the fine scale part of it and substitute the fine scales from the previous slide in here. Now, one attribute of the stabilized methods is that it allows us arbitrary combinations of interpolation functions for the unknown fields. And so we opt to use piecewise constant L2 projections for the Lagrange multiplier and locally solve this problem segment-wise. And we get segment-wise expression for Lagrange multiplier as weighted stress at the boundary and the jump in the displacement field. Now, important thing here to realize is that tau, the derivation of tau, I showed you on the previous slide, and the weighting parameters from either side, they are fully derived in terms of tau. And this weighting flux is also going to account for the material mismatch across the boundary. When we substitute this derived lambda and u primes into the coarse scale formulation, we get a general structure that we see here. This same structure that I showed you on the third slide. These are the domain interior terms. These are the continuity of the balance of flux, continuity of the displacement field, stabilized form, stabilized term for the jump in the displacement, and stabilized term for the jump in the flux. So features of Niche type method are present in here. But in addition, the parameters are fully derived, and they are consistently derived. They accommodate element size, aspect ratio, shape of the element, polynomial order, material properties. All the features are naturally built in these parameters. So now let's try to evaluate with this formulation. Here is a simply spotted beam for which we have an exact solution. We make a mesh of T3 and Q4 elements, no node on node contact, two different type of elements. And here is the rate of convergence for T3, Q4. Linear order elements, so rate of convergence ideal is 2, according to finite element theory. And we get a rate of convergence of 1.97 in here. And for the case of Q4, Q9, we are getting a rate of convergence of 2 because it's dictated by the rate of convergence of Q4. And for T6 and Q9 elements, we have a rate of convergence of 3. and H1 is 1 order less. So this shows the variational consistency, numerically shows variational consistency of the formulation. As I mentioned, that our objective is to couple different PDEs, and so in that context, let's take mixed form of elasticity, displacement form of elasticity that I just talked about, and mixed form of elasticity that brings in one more unknown, which is the pressure field. So this is domain interior governing a part for this portion for the mixed form. And we impose the continuity of the flux and the field through Lagrange multiplier. And the idea is exactly as we did. We are going to follow the same line of thought. We will split the scales, the displacement field, from the displacement form of elasticity and mixed form of elasticity into coarse and fine along this interface. That gives rise to fine scale problem at the interface. We are going to locally solve for the fine scales. And when we do that, we get fine scale expression coming from the displacement part, fine scale expression coming from the mixed part. And we can see that they are proportional to the residual of the flux at the interface. And the flux is and A2 is the domain boundary operator, which is related with the domain interior operator, which has the mixed form of constitutive model fully embedded. So physics is all preserved all the way to the interface. Now that we have U1 prime and U2 prime, we can now go back, exploit the continuity of the underlying field, displacement field, and locally solving for the Lagrange multiplier, we get an analytical expression for lambdas, where taus are analytically derived and weighted fluxes are analytically derived. So VMDG formulation looks as shown in here. These are the DG terms. These are the additional terms that are derived. The stability parameters have a weighting of area weighted and stress weighted embedded in there. And this weighting flux term is better suited for material mismatch when we have stiff and soft material next to each other. This framework can also be used in domain decomposition strategies where we split a large mesh into smaller segments on distributed computing platforms. We can use these methods for integrated transfer of information. Now let's look at convergence rate study with this formulation where we have used mixed form of elasticity in the middle and displacement form of elasticity on the two sides. We are using Q4 elements and Q9 elements, no node on node match, and also the number of unknowns across this interface are different. Let's look at the rate of convergence for the case of T3Q4 element, T3Q4 element rate of convergence of 2, H1 is 1 order less. And for the case of Q4, Q9 elements, rate of convergence is dictated by Q4 elements is 1 and H1 is 1 order less. So variational convergence, even when we have different element types, no node on node match and different governing equations across the interface. Now, from a method development point of view, the question that comes up is that we are talking about multi-field problems. Each comes with its own governing balance laws with its inherent spatial, material, and temporal scales. So this error estimator should also be scale aware. Does this framework have an error estimator that can account for scales? So from that point of view, let's revisit the additive decomposed form of the displacement, and we can rewrite it that we now got the solution U bar with the stabilized method. So it is better than the Glerkin method because missing physics is embedded in it. However, we are still solving it numerically. So any difference is the error. Error has two parts, a global error and a local error. So local and global errors are there. Local error can be quickly calculated by going back to the element level and finding U prime. That is a local distribution of error, and it tells us how good was our approximation of the bubble, or how good was the bubble function in presenting the fine scale error. There, in solid mechanics or in fluid mechanics, there are always global pollution error that is present there. For example, if we model this cantilever beam with 4 node elements, the elements are going to respond in shear. So the beam will inherently have a stiff response if you do not do enough mesh refinement at the root section. So this parasitic shear will set in. So this is a global error that is going to be there all the time. And we can now look at the total solution, which is a part that we computed and a part that is error. We substitute that in the governing equation, and we realized that UH and PH, which were the solution, they knock out the source terms because we got the solution based on those source terms. And what we are left behind in our variational equation are these terms. We take the terms EL, which is local error, which we can just do calculate by a simple back solve over all the elements, and take all the terms where EL appears to the right-hand side. And we realize that on the left-hand side, we are left with the same factored stiffness matrix that we used to solve the problem. So if we hold the stiffness matrix and just make the new right-hand side with the local error in these terms, just a forward solve of the same factorized stiffness matrix gives us the global error. So it's a very cost-effective estimation of the total error in the solution. Now let's look at the convergence rates. This is convergence rate study. Standard with error means that evaluated with respect to the exact solution, and local explicit with respect to the residual based. And we get for T3, T6, or Q4, Q9, the rate of convergence in the H1 is dictated by lower order elements, and we get rate of convergence on 1. And for T6, Q9, which are quadratic elements, H1 should be 2, and we are getting rate of convergence of 2. So this local explicit error not only provides a rate of convergence at the estimate of the error, variation consistency of the method, it also provides the spatial distribution of the error. So this is standard error means with respect to the exact solution. Local explicit means we have not used the exact solution here. Rather, this is based on the residual based estimate. Now, let's look at how does it do for mathematically non-smooth problems, because whenever we have interfaces in mathematical problems, these are going to be mathematically non-smooth problems. It is a problem which has singularity in stress or in pressure field. And if you're doing global refinement, the rate of convergence is dictated by the order of singularity and is the maximum value is 0.545. Here we are showing the L2 norm of the error for Q4 elements. Standard means with respect to the exact solution, and explicit means residual based error estimate. And we see a convergence with a rate of 0.7. And here is the H1 of the displacement error, 0.56 and 0.54 H1 norm. There is also an implicit. Implicit means we can add the total error. So explicit error is a very cost effective. You only do a back solve at the element level, and you can very quickly get the variation features of the method or the variational convergence estimate of the method. Now, we are living in the age of big data, and question is, does this framework that I'm presenting here, does it accommodate data? For example, let's say this is a domain on which we are want to solve subject to some body forces, fractions, applied displacements. And suppose we have a sensor that provides us precise information about the displacement field in a certain region, and it's only a small region where we have high fidelity data. Question is, can we model this problem and can we drive this problem not only by the governing equations, but also the data that we know about that tells us about the behavior of the system? For that, we focus on these two terms that we derive through VMDG formulation. And to keep the thing simple, I will focus on this, the stabilized term for the displacement continuity. So depending on the data that we have here, high fidelity data and numerically calculated value, the difference between two is our error, the residual. So we can make an error function and embed that error function into this term, jump in the displacement, and this becomes our objective function. And we can show that this objective function can be derived from an underlying loss function, as shown here, where tau, that is analytically derived, behaves as a kernel function. So it provides us the feature of embedding sensor data into our variational framework. So now let's look at this problem, where we had mathematically non-smooth problem, where we have used T3 elements, Q4 elements, no node-on-node contact, and displacement form of elasticity and mixed form of elasticity here. And suppose that we have high fidelity sensor data in this domain here. And so we are using sort of the exact solution as our representative surrogate high fidelity data. So we are using data here and see how does it affect the overall quality of solution. This is the convergence rate for this problem with this non-matching meshes, different element types without sensor data. And when we add the data, we get substantial reduction in the, and also improvement in the convergence rate. Here is the H1 norm of the error, the simulation without embedding the data, simulation with embedding the data. Now, here, let's look at different data types. For example, we may have sensor data in one place which is close to singularity or somewhere away from singularity, or we could have a discrete data along the edge, not a distributed data. So there are three different scenarios. And for each of these scenarios, we have plotted comparison without the sensor data or the three cases. And each of these three cases substantially reduces the error overall in the domain. Here is the H1 convergence, and we see same feature, optimal convergence rate. And each of these different ways of embedding data, distributed data or discrete data, reduces the error substantially. And what you can see here is that we are able to get the same quality of engineering solution as we would otherwise get with substantially refined mesh, considering if the method is variationally convergent. Substantially refined mesh will give us the right physics, which we can get even with very crude discretizations. So this is some ongoing work in this area. And there are avenues that we can also embed the data on stresses, which are going to be the gradients of the fields. So now that we have talked about different attributes of the method, let's look at, does this method accommodate discontinuities, evolving discontinuities? For this, we go to finite deformations. So this is a momentum balance equation or energy equation for the evolution of the temperature. So we enforce, if we cut the domain, so we have to enforce the continuity of the field. Now it is going to be in the context of mappings. And if we want to keep the provision for interfacial debonding or sliding, then we add this gap function. And this gap function provides us an avenue to bring in interfacial models. In micromechanics, there are beautiful models that have been developed for polycrystalline materials, for engineered materials at slip planes. So we can bring all that knowledge base through this avenue into our calculations. Likewise, for the thermal field, as we cut the functions, we have to enforce the continuity of the temperature and its flux. So now we have two Lagrange multipliers that we need to solve for, one for the mechanical part, the other one for the thermal part. And the idea is similar. We decompose the solution into coarse and fine along this interface. We will have one part coming from mechanical, the other one from thermal, locally solving for the fine scales on either side for the mechanical part, locally solving for the fine scales for the thermal part, and then solving for the Lagrange multipliers. We get this thermomechanical interface formulation, stabilized monolithic formulation. In one fully coupled form for fashion, we can get convergence. And this formulation is exactly, we can linearize it, so we can get quadratic rate of convergence in Newton-Raphson method. And that is very attractive attribute for nonlinear problems, especially when it is highly evolving nonlinear phenomena. I've written it down, simplified it. Mechanical part has the Galerkin part. This is there in the standard Galerkin finite deformation framework. And this is the interfacial part that can be derived through the framework that I presented. Likewise, for the thermal formulation, the standard Galerkin form and the interfacial form. And this interfacial form is also fully coupled because the mechanical, the thermal evolution needs to have information about the mechanical information fully embedded in it. Here is a thick wall cylinder, temperature and pressure applied on the inner surface. Material properties are shown here. These, we have plotted the temperature, evolved temperature profile on the geometrically deforming surfaces. Here is the temperature evolution on the inner surface for two different coefficients. This is a highly interactive coupled response, and we have compared with C1 Armaro all the way through the deformation mode. Now, in this particular case, we have two different materials, outer ring. So we have an interface that goes in the radial direction, an interface that goes in the circumferential direction. And outer ring is a material which is 1 order of magnitude softer than the inner. And we are looking at, we're plotting the radial stresses along this line in the radial direction. And we see that exactly at that point, we see a jump in the stress between. So we are able to capture these features very accurately in this class of problems. It is an application to progressive debonding under transverse loading. At the interface, we have embedded Taylor-Cunningham model. It's fully adherent And once the stress exceeds a certain level, the debonding takes place, which eventually leads to cracking of the matrix. So debonding, cracking of the matrix starts total failure. And here's the comparison with some published results. Here is the case of multiple inclusions, stiff material in a relatively soft matrix, 3 different meshes, and comparison with experimental data. So with this in hand, now that we have a method that can do deal with layers or discrete representations, let's use it for additive manufacturing, layered additive manufacturing. The technical issues involved are that material properties evolve, interfacial bonds evolve. Under mechanical loading, these interfaces can fail. So our method to begin with should be able to account for these kinds of features. And from the material science perspective, there is material evolution as the material cures, and as the process, additive manufacturing has intricate link between the manufacturing process and the property evolution of the material. So along the way, if there is any material instability, that can trigger geometric instability. So the method has to be written in the finite deformation context to be able to do these kinds of problems. In our model, we are using a modified form of Drucker-Prugger model, a hyperelastic extension, where hyperelastic model is shown here. And the yield function is written in terms of first invariant of Cauchy stress, I1, and J2, which is a second invariant of the rhetoric part of the Cauchy stress. And the modification that we need to do is shown in here. In the case of additive manufacturing, as the material cures, and this is typical for, let's say, cementitious materials, if we focus on that, that is what we are focusing in this current work. As the thick cement paste comes out of the nozzle, its mechanical deformation freezes there, and its material properties evolve. So under a constant stress, for example, if we look at this model problem, if the modulus of elasticity increases, this reduces the deformation under the constant stress. So this elastic recovery, which is non-physical for the type of problems that I'm talking about. So this is the bounce back that takes place under constant stress when the material gains strength. In order to address this, we have developed this algorithm. At the integration points, we do a decomposition of the stress. We compute the elastic strains, compute the stretches, and reconstruct the Cauchy green deformation, left Cauchy green deformation tensor. BE is related with C plastic inverse. So in a way, this corresponds to a projection techniques that preserves the shape and lets the material evolve. Here is the experimental observed values of stress strain plot for cementitious materials, 0 minutes, 50 minutes, 30 minutes with time. And here's the corresponding increase in strength. We have applied load, and if we do not have, so these colors here show the increase in the modulus of elasticity as the material cures. And if we do not have bounce back control, then material also unloads itself or recovers its shape. And with the bounce back control, we are having a material evolution at the same deformed geometry. And this is the corresponding case for the case of shear, where the material gains strength at the shape in which it was poured. Here is the method. It is I call it ghost mesh method, where we have made the mesh to begin with, and we have a point that moves in the domain and identifies which element and which of the integration point layers is being printed, and it accounts for that in this layer-wise process. So nozzle trajectory is a part of this process where the material is evolving, and we can see the earlier layers that were placed earlier, their modulus of elasticity is increasing as a function of time. And here is the experimental data, and we can see that this geometric deformation along the edges, and here's the geometric deformation for this printed hollow cylinder in the lab, and we can sort of see similarity in the mode that are captured here. So now let's take a look at another interface problem, which becomes very interesting. Again, it falls in the same framework that I talked about. We have an interface across which the equations change. We have hyperelastic solid in this domain 2, and incompressible fluid across the domain governed by Navier-Stokes equations. So rather than having node-on-node contact of the underlying variables, we are going to use VMDG approach to develop an interface capturing or interface modeling for fluid structure interaction. And that can provide us flexibility in terms of making meshes for the two domains independently. And this becomes very important in patient-specific geometric modeling of the materials. So here is the continuity of the field and continuity of the flux. V is the velocity field. We developed the Lagrange multiplier formulation. Now, across the interface, we have the velocities from fluid and solid. Across the interface, we have fluxes coming from fluid and solid. So we are going to embed them through here. So we do a multi-scale decomposition of the velocity field. This gives rise to a coarse scale problem and a fine scale problem. Fine scale problem has Lagrange multiplier enforcement of the flux at the interface. Fluid will carry the normal pressure, and the solid can take normal and tangential. So we solve for it, and then piecewise resolve for the Lagrange multipliers. We get the solution scheme. So solving for the fine scales in the fluid, we get the fine scale velocity, which is proportional to the residual at the boundary in the fluid, and likewise fine scale incremental displacement for the solid, and it is proportional to the corresponding residual at the boundary. Now, in order to derive the Lagrange multiplier, we go to the continuity equation that says there should not be any gap at the massless plane. So continuity equation has jump in the velocity, coarse and fine. We open the fine terms and substitute these expressions, assuming piecewise constant projection of Lagrange multiplier and solving it locally, segment-wise, we get this expression. Substitute it in the coarse scale formulation, and we get this form here. And what I want to highlight is the general variational structure. The first two terms here are the terms from the Galerkin method. The next two terms are the continuity of balance of flux and continuity of the velocity field. And then we have these two terms that have come in. They are imposing, stabilizing the velocity field and stabilizing the traction across this interface. Here is the an example problem. Flow comes onto the cylinder, gives rise to vortices that excite this motion of the very flexible beam. Along this interface, there is no node-on-node match. And so we need to integrate the terms, the interfacial terms across this interface. And this is the scheme that is used. What I want to point out in here is that along this interface, we have plotted the stabilization parameter. And you can realize that even in the same simulation, stabilization parameter adjusts its value locally, adaptively, as a function of space and time, so that variationally, consistently, it solves the problem. And so for these types of problem, if you are using Nietzsche method and we pick a stabilization parameter or Nietzsche parameter of one constant value, that value will work for certain Reynolds numbers, but as you go to high Reynolds numbers, the chances that will blow up are very, very high. So using a method which adjusts itself according to the evolving nonlinearity is a rather appealing approach. With this in hand, we can now look at another perspective. We can look at one-sided VMDG. I talked about VMDG for solid on both sides with different governing equations, fluid-solid interface. What if we have nothing on the other side? So we have this object and a boundary which is not aligned with the mesh, and we can apply this one-sided VMDG method, and we can get frameworks for additive manufacturing where we have material and outside there's nothing. So we can embed the boundary conditions, essential boundary conditions, in an immersed scheme as shown in here, and this provides tremendous flexibility in additive manufacturing. We can do the same thing for the case of fluids. There is a cylinder, and the surface of the cylinder is cutting through the elements, and this provides flexibility in terms of doing flow calculations around immersed objects. As in the last few minutes, I will like to talk about another class of problems in fluid mechanics, density stratified incompressible flows that have mechanical equations and they have energy equation. And these are all fully coupled and coupled in the context of turbulence. So these scales are present both in mechanical fields and thermal fields in space and in time. So the question is, can we use hierarchical VMS framework to derive a model for density stratified turbulence? This is a paper that has just appeared in CMAME. And so we look at it, we do a scale decomposition of the field, of the velocity field into coarse and fine. These are now overlapping scales, and pressure field into coarse and fine, and these are overlapping, and temperature fields. So we have resolved scales, U bar, P bar, and theta, and we have fine scales, U prime, P prime, and theta prime. And at this point, we develop the resolved, so resolved scales are going to be fully linked in the coarse scale problem. We develop the fine scale problem, and fine scale problem also needs to have the link between the fine scale physics, because it then provides a very tightly coupled fine scale model that tells the coarse scale model about the missing physics. And then we embed both of them through VMS framework. This provides fully coupled turbulence model, and I'll show you some numerical results with that. So the idea here is we have this velocity, pressure, and temperature fields. Through VMS, we decouple them into coarse scales and fine scales. And we do a hierarchical decomposition of the fine scales into a velocity scale level 1 and level 2, and temperature level 1 and level 2. It is not necessary that we do a scale separation for every field to be able to develop a stabilized method using the VMS approach. And the objective here is that the second scale separation provides us a mechanism when we embed these scales back into level 1. It provides us a stabilized form for level 1, so which is not dictated by the in-soup condition, and therefore it provides us an avenue to be able to derive expressions for U1 prime, P prime, and theta prime, and that will be our model, closure model for density stratified flows. So with these two, so there is one application of VMS, scale split, a subsequent split of scales, and now we build the physics back. This gives us a stabilized level 1 system of equations, and embedding this back is the closure model that we embed into the governing system of equations comprised of generalized Navier-Stokes equations, momentum balance equations, and the energy equation for the fluid. So now let me show you some interesting problems. This is Rayleigh-Bénard convection, hot plate at the bottom, cold plate at the top, and gravity is acting in the opposite direction. Here is, we are looking in the wall normal direction. This is a space-time fluctuation of the temperature field, and we have compared present work with the DNS results and LES results published by different authors. Here is the history of kinetic energy, and once the flow fully develops, the response from the present method is in agreement with LES and DNS results. Here is space-time average fluctuation of the vertical velocity, again, present results with LES and DNS. And here is the history of entropy. And again, once the flow has developed, we get total entropy is same as that in DNS. And the present calculations are shown with 64 element cube mesh, whereas the reference results or DNS results are on substantially refined mesh. The LES results are on substantially refined mesh. And we are using 64 B8 elements, linear break elements for this problem. The last test problem is turbulent correct flow. There are periodic boundary conditions applied in the span-wise direction and the lateral direction, and prescribed temperature and velocity on the top and bottom surfaces. They are moving relative to each other, and gravity is acting vertically. This is the complicated, involved flow features. This part of the domain shows the velocity profile on top and bottom, and on the right side of this plot, we have plotted the temperature boundary condition. So in one plot, we are trying to show both of these. Velocity boundary condition on top and bottom, and temperature boundary condition on top and bottom, and the fine scale structures that appear in these calculations. There is the wall normal streamlined velocity and wall normal statistically averaged normalized temperature. And again, good correlation with DNS results and LES results. Here is the turbulent wet flow, second order statistics, streamwise velocity fluctuations, and comparison with published results, temperature fluctuations, turbulent heat flux, and turbulent shear stress. And we have solved this problem with two mesh refinements, 64 cube mesh and 128 cube mesh, whereas DNS results is on 512 to 57, 512. And our fine mesh provides very good correlation with the DNS results. So as my concluding remarks, I would say, I've presented a variational framework for consistent coupling of multiple PDEs, whether they are across the interface, as in solid mechanics, multi-constant materials, or in fluid structure interaction, or they could be overlapping, as in the case of turbulence models. The framework accommodates sharp and diffused interfaces. It is applicable to a broad range of problems in mathematical physics. I've tried to show several example problems, both in fluid mechanics and in solid mechanics. And as I mentioned, that in this EMI conference, there are symposia looking at these problems, either purely from fluid mechanics point of view or solid mechanics point of view. So I think these methods would provide you some interesting aspects to modeling or method development. Fine scale feature of VMS is not just a feature to stabilize the formulation. What I wanted to highlight here is it is a method to embed missing physics. And interface coupling operators that arise, they can also be used for multi-grid patching. These operators fully account for element size, aspect ratio, shape, polynomial order, material properties. They're fully represented and they are variationally derived. You can use these methods for coupling dissimilar PDEs across the interfaces. You can use it for non-matching meshes, whether fluids or for solids. I've also presented a residual-based error estimator presented in the context of elasticity, showed that it works for finite strain elasticity. The variational structure of the method has linear regression inherent in it, and the structure of the terms that I derived, they can be used to embed loss function, and that can help if you have high fidelity data, but is in a small location in the overall spatial domain. You can use that high fidelity data in a variational context so that it does not upset the variational structure of the underlying mathematical method, so that you can get a solution that can give you better accuracy on cruder discretization, or it can help you reduce the uncertainty in terms of the modeling parameters. And hierarchical application of VMS results in residual-based closure models for larger dissimulation. I would also like to acknowledge my collaborators with whom I've enjoyed working in my career, and the problem classes that I presented here, funding agencies and computer resources provided by different centers, for which I'm greatly obliged. And with that, I thank you all.
Professor Masud, thank you very much for a very inspiring lecture. The floor is open for questions. Okay, I'd like to start with one question myself, if I may. You mentioned how you could inject data into your formalism. Well, the data that you're measuring was data measured from the exact operator that you're solving. What do you think may happen if you're measuring data from a real experiment?
Yeah.
Could that be used to further stabilize your algorithms?
Yeah, very nice question. In here, I was showing a model problem where we are saying high fidelity data, very small amount of data, but high fidelity. So we used exact as surrogate data to embed it. The main idea here was to show that if we want to embed data in physics-based models, the best way is to inject it in a variational context and in a method that variationally accommodates this idea. Now, if you have data that is coming from experiments, and if that data is providing, obviously it's going to provide some information about the system, the main thing over there would be that we have a mathematical idealization when we are developing with a model problem and boundary and initial conditions. There is an idealization in there. And that idealization inherently assumes that the system from which you are getting experimental data, for example, if you have fixed boundary condition, then that system also has boundary conditions as closely applied. We know that there is nothing fixed in the real world, but it is as closely applied. So if your physical system, the parameters, the constraints of the physical system are close to the constraints in your underlying model, then the data from that sensor-based data that you will embed it will be variationally embedded, and it should maintain that consistency.
Thank you. Very interesting. Do we have any more questions from the audience?
I have a question, if you don't mind.
Yes, please.
Thank you very much for your nice presentation. For the case when you consider the flux or the traction jumps across the interface, what kind of traction separation law do you adopt in your method?
For example, there was example problem of Taylor-Kuhnian model that we had shown there. So it is like a plasticity type model, which initially starts with a fully bonded surface. But then once a threshold is reached, after which there is a gap function can increase. And depending on the model, once the gap function increases a certain value, so that is where your local model, mechanics-based models, and there are many models people have developed, comes in. And as the gap function increases, the intensity of force, how the two parts are put together or they feel each other, that intensity starts going down. So you can bring in all those models in this framework that I was presenting. So the model, to answer your question, the one that we used was a fairly simple model for debonding.
So do you treat the interface as a separate element, or you just calculate the jump fields using the bulk elements?
No, it is just the interface. There is no separate element in there. So the coupling is coming from a mathematical point of view. And that is the beauty of this method, that you do not need to have spring elements there. You do not need to have motor elements in there. It is exactly the functions that you derive at the interface. Those are the functions. And I showed you that those functions are proportional to the residuals, and the residuals are a function of your constitutive model. So whatever constitutive model that you are using in the multi-material on either side, that is fully represented all the way to the boundary. There are no springs in this entire presentation.
Thank you very much.
Right, we have time for one last question.
Okay, I will ask a question if nobody wants to ask.
Yes.
First of all, really very nice presentation, Arif. And what I like is the mathematical rigorous in your models. I think this is beautiful.
Thank you.
A couple of very quick questions. The first one is, I guess, related to the question that was asked. So I think this is your interface model. When you have debonding, is essentially related to what is called cohesive zone models, where you can embed different cohesive traction separation functions. So it could be interesting to kind of explore your method as compared to cohesive type methods. There are some problems in cohesive type methods. For example, you can see some oscillations and things like that, where I think your method can overcome this. So this could be very nice. But this I wanted to ask you, this is question one. And question two, when you solve the thermomechanical problems, you had two Lagrange multipliers, one for the mechanical part and one for the thermal part. I was just curious, when you have the two interfaces touching each other, why do you need the thermal Lagrange multipliers? Because the materials are touching, and so the heat is automatically transferred due to contact.
Good questions. Let me answer the first one. The interfacial stabilization actually provides you a very stable interface. And so if you have cohesive models or any models that have local stress singularity, This method will provide you stability of your numerical scheme. So if you're solving a numerical problem that has physical instability, then your numerical method should be very stable to be able to follow the physical instability. And this method will provide you that feature. The answer to the second question is that we were looking in a larger context where there are materials with different coefficients of thermal conduction. So there is thermal, for example, take a look at the solid rocket propellant, where it burns at a very high temperature and there is a huge temperature jump across the interfaces. So we wanted to develop a method which not only accommodates the physical discontinuities, cracks in all directions, but can also accommodate jumps in the temperature field. Temperature equation looks very benign, but in the nonlinear context and when written as an advection equation, it can completely kill the numerical simulations because of the instability in the temperature field by itself. It also can have convective terms, and because of a mismatch in the coefficients, although in linear diffusion phenomena, heat equation helps you out in the numerical calculations. But in the type of problems that I mentioned, it can otherwise destabilize stable mechanical problem. So we wanted to have both the features.
Thank you very much.
Thank you. We do have a few more questions, but we are out of time, and we need to stay on schedule. Thank you again, Arif, for a very inspiring and interesting presentation, and good luck with the remainder of the conference.
Thank you, Roger, and thank you, everyone.